Hello there. Welcome to our today's science lesson. The topic for the day being planning for an experiment. You realize that in our previous lesson, we looked at how one is supposed to write a scientific report. And for you to write a scientific report, it means you should have done at least an experiment, so that from that experiment you can now be able to write that scientific report. We even went further to do a rough way on how you are supposed to write that scientific report, putting in mind that our aim or our point to prove was to look at how different beverages can undergo cooling in different rates in different containers with different maybe composition. And I remember having asked you, when you go home or wherever you will be, you can as well carry out that experiment to maybe confirm some of these facts on your own. Remember, some of these things are usually consumed by oneself. Like now, to know which beverage to go for, it is your own consumption. So it is you to do the experiment, get the results, and go by the results. But there are things we didn't go into in detail when we were looking at that way on how to write a scientific report, and also on when we were looking or going through that example of an experiment on the cooling or the rate at which beverages cool. Today, I want us to look at some of those things. Small they may look, but very important, because those are the things that make an experiment look to be an experiment. So on what you did, you may have made mistakes without realizing. On what we are going to look at today, you will see whether you either made a mistake or not in one way or another during that process of testing which beverage undergoes cooling faster than the other. Was it coffee? Was it drinking chocolate? Was it tea? Was it whichever beverage you used? And these are: one, we have, when planning for an experiment, the following aspects are supposed to be checked on and followed strictly. And that is: one, identifying variables. We have number one is identify variables. You identify variables. Now, when you talk about a variable, you need to realize that in any system, in any experiment, in any aspect of concern somebody is trying to check on, there are things in it that could be varying with the time, but there are those that will not be varying. There are those that cannot vary in whichever way you may wish them to vary, they will not vary. But there are those that will vary depending on the way you want. But again, there are those that can vary, but you may make them to be constant, not to vary. So we are looking at three aspects here: variables that can be made to vary, and variables that can be made to be constant, that is, not to vary. And number three, non-variables. Three issues. So I will start with number one. I will look at the variables. Variables. When you talk about a variable, a variable can only be called a variable if it is depending on another one. You can only call an aspect a variable if it is depending on another one. So we call them dependent variables. Dependent variables. A dependent variable is that aspect that changes only when the other one changes. If the other one does not change, then it cannot change. And I will use the very experiment we used in the previous lesson before I bring in a new one. In the previous experiment, we were talking about cooling of beverages. Let's look at this coffee that you want cold before you take to avoid maybe an injury. Are there any variables that were being involved? Indeed, there were so many. One was the shape of the cup. You have this shape, or you have this one. This is a variable you are bringing in, the shape of the cup. The material the cup is made of, the material the cup is made of. If it is light or if it is thick, it will obviously affect the rate at which this beverage will be cooling. When you say here there is sugar and in this one there is no sugar, that is a variable. And that variable will cause the whole reading of the experiment to be different. Now, when you bring in the issue of you are varying the type of material, you are varying the shape, you are varying the composition of that beverage, all those will be varying the rate at which the temperature will be reducing from that 90 degrees centigrade we had picked on to, let's say, 80 degrees centigrade we had also picked on. We talked of 80 or 85 degrees centigrade. So for that temperature to drop from 90 to 80, you have to look at those variables that will be affecting that temperature drop. Now, this shows that temperature is a dependent variable. Temperature here is a dependent variable. If you don't change the shape of the cup, then the drop in temperature will still be as it was previously. There will not be any change because you haven't changed anything. But if I change the shape of this cup from this to this, then the temperature will depend on the shape of the cup. The temperature will depend on the shape of the cup. The temperature will depend on the material that was used to make the cup. The temperature will depend on the composition of this cup. So we say temperature is a dependent variable, but we also have some other changes that will go on whether you change the material or you don't. And those ones are called independent variables. So we have here, I will use D to mean dependent variable and I to indicate independent variable. We have a dependent variable and independent variable. I've just talked about a dependent variable, and an example here is temperature, which was depending on so many other aspects for it either to drop very fast or to drop slowly. But we have another one, and that is an independent variable. This one is a variable that will always vary whether something happens or it doesn't. It will always move. And that one, going by the previous experiment you worked on, is time. Looking at time. You are checking on how long will this beverage cool from 90 to 80 degrees centigrade by varying some of the aspects. But look at the time. Whether you vary, you don't vary, you add in anything like those sugar crystals or you don't, you change the beverage, you don't change the beverage, time will always move. So here we say time is an independent variable. Time is an independent variable. So you have to be aware of these variables when setting out or when planning to have an own experiment. Then lastly, we also have what we call controlled variable. Controlled variable or controllable variable. Controlled variable. Now, when you are talking about a controlled variable, this is similar to the first one. This one was dependent, so it is a variable. But time cannot be varied. So an independent variable. So dependent variables can be more than one in an experiment. If they are more than one, there is no way you can investigate them. What am I trying to say? When carrying out an experiment, you carry out to test the dependent variables, to look for dependent variables, to look for effect of dependent variables. And when looking for these dependent variables, they can be more than one in a particular experiment. An example here we said you can pick on material first, then pick on the shape first, then maybe pick on a different issue, the concentration, second, third, fourth, etc. So that is a dependent variable. But since there are always more than one dependent variable in most cases when carrying out an experiment, then we have to bring in what we call controlled variables. Then what is a controlled variable? This is a variable that is dependent, but you make it to be constant. You make it to be constant in all the tests you are carrying out. Let's have an example here. If I'm comparing the cooling rate of coffee to that of drinking chocolate, the cooling rate of coffee as a beverage to that of drinking chocolate, it will be unrealistic for me to use, when cooling coffee, I use a V-shaped cup, and when cooling drinking chocolate, I use such a shape of a cup. And yet, I want really to test to find out the time it will take for each of these beverages to cool from 90 to 80 degrees centigrade. Obviously, we know that the shape will have an effect. Whether it will increase or reduce the speed at which it will be cooling, it will have an effect. So which means, by getting the time at the end of it all, explaining, analyzing that data will be difficult. How will you state that? Is it because the shape was different, or is it because the beverage was different? It will be hard to tell. For you to be able to explain the difference in the times you will have gotten at the end of the day, the shape of the cup should be the same, or the beverage should be the same. That is, you will have put one of the dependent variable to be constant. Let's have a good example using the previous one here. I can say, determining the rate of cooling of coffee, the rate of cooling of coffee from 90 degrees centigrade to 80 degrees centigrade by using a heavy mug that is V-shaped. a heavy mug that is V-shaped. So I'm talking about the beverage being coffee, and the other material that I'm using is a heavy mug, and the mug is V-shaped. Talking about the beverage, it is just coffee. How about the mug? V-shaped. Again, I'm talking about another beverage, which is drinking chocolate. But still, I'm using the same heavy mug that is V-shaped. Since the volumes are the same, we say that, because remember, volume is also a dependent variable. Temperature will depend on the volume. You don't expect too much of the beverage in the cup to take the same period as very little of it in the cup when it comes to cooling. So that's also another dependent variable. So I'm having 200 mils of the same. At least at this point, now I can comfortably get the temperature variation of coffee from 90 to 80, of drinking chocolate from 90 to 80, then be able to analyze my results, then have a realistic conclusion. By having maybe seen, just an example, that maybe coffee took 15 minutes to cool, and this one maybe took 9 minutes to cool. You will have known that that dependent variable of volume was constant. That dependent variable of having same type of cup was constant. The only thing that was varying was the type of beverage. That is what one is supposed to do whenever you are planning for an own experiment. Check on these three aspects. Check which type of variables are present in that experiment, all of them. All the variables, dependent variables that are present. Then, pick out one variable at a time for testing. Pick out one variable at a time for testing. After picking out the variable of interest, all the others, make sure they are put to a constant. Design the experiment such that all the other dependent variables are constant. Then lastly, identify the independent variable that is at play in that particular experiment. And you will find that in most cases, you will find that independent variable, in most cases, not all cases, but in most cases, is usually time. After having gotten all of this, then you will have to develop a hypothesis. We are trying to plan our own experiment. So after you have done all of this, you have identified the variables. The second one is you have to develop a hypothesis. You develop a hypothesis. So when developing a hypothesis, as I said earlier in our previous lesson, that a hypothesis is just kind of an educated guess. It's a guess. I think when I do this, this will happen. The guess might be right or might be wrong. So maybe to understand from the development of a hypothesis and downwards until we make a conclusion, I will wish us to look at another experiment, not just to base on the previous one. I want us to pick on a very easy experiment, which maybe being a student, you should not just rely on just classwork. You also need to make yourself active on the pitch to make your body fit. So probably you are a tennis player. I'm sure if you are, you must be smiling, and that is good of you, because you need always to be physically fit as well as mentally fit. fit. Now, for you to be fit in that tennis court, you want to test whether that tennis ball is good or not. There's something probably you normally do. You bounce that tennis ball on the surface. You bounce the tennis ball on the surface. You can even use the racket to hit the ball to a certain height. When you bounce that tennis ball on the surface, there is the way you will drop it, then it will bounce back to a certain height. If it bounces to a certain height, you will obviously conclude that this ball is good. Or if it doesn't reach that height, you will conclude that the ball is bad. It does not qualify to be used. So I want us to take it as an experiment. So what does it tell us? When writing a report, we say that the purpose comes out to be the first one. What is the aim? What is the purpose? To check on the height. Our experiment now, we want to design our experiment. What is the aim? What is the purpose? To check on the effect of the dropping height, the dropping height of the tennis ball, the dropping height of the tennis ball related to the bouncing height of the same tennis ball. If you drop this ball to the ground, it will obviously bounce back. So we want to relate the dropping height of the tennis ball to the ground in relation to the bouncing height of the same tennis ball. That is our aim. That is the purpose of our experiment. Then after the item has been given out as this is the aim, what you do next, you have to look at maybe the materials and all that. The material here we are talking about is the tennis ball. We also have the surface, is a material. Remember, you can bounce the ball on a hard surface, concrete surface, a wooden surface, a soft surface, any other surface. So this also qualifies to be a material. Then we also have what we call the procedure. When it comes to the procedure, you will have to state at what height will you be dropping that ball from. You can design such that you can move from maybe 3 meters high as you move down until you reach maybe 0.5 meters high at a drop of every half a meter. So that is 3 meters, 2.5, 2 meters, 1.5, 1 meter, then lastly 0.5 meters. As you carry out your procedure, you will have to record the results. But now here, before we reach at that point, let's go back. After getting the title, the heading, the aim of the experiment, we had to go for a hypothesis. And that's where we are. I jumped that part intentionally because that's the point we are discussing at the moment. So after you have gotten the aim of the experiment, before the aim of the experiment, you will have obviously done all of this. Identify the variables in that experiment of yours to see if it is fit. Then out of that, you now narrow down to a particular dependent variable. So my dependent variable here, my dependent variable in this experiment of mine is, does the dropping height of the tennis ball affect the bouncing height of the same ball? That is my dependent variable. But there are other dependent variables that will be made constant what we call controlled variables. An example is the surface on which you will be bouncing the ball. 2, the type or the material that was used to make the bouncing ball. 3, how do you release the ball? Do you push it or do you just release it? It's different. I can throw it, but at this particular height, I push it. Or I just leave it to drop. Those are two different ways of releasing the ball. That will be a variable that I will make constant. I can decide all of them will be released. So I've made the point of release to be constant. That will be a controlled variable. The material used, let it be of the same material. The surface onto which it is bouncing should also be the same. I will have controlled all the others, only one that will be left, the height at which you will be releasing down as you move up to, maybe an example is 3 meters. So from there, I can make now a hypothesis in my experiment, having made all the others clear. And the hypothesis can be, I think, increase in the dropping height of the tennis ball will increase the bouncing height of the tennis ball. If it is right, whether it is right or wrong, I don't know. I can only confirm it through an experiment. So after the hypothesis is when now you go in for the materials, pick out the materials following the variables as you had identified. Then from there, you go to the procedure. With the procedure, using the different heights, you carry out the experiment and record the data accordingly. So I will wish we get a rough idea of the data from our measurement and the observations that we'll have made from the procedure as we have stated, so that we can be able to use it when it will come to also doing the analysis and maybe a conclusion of the same. So let's look at a table. We look at a table on how we can record. Now remember, in our previous lesson, when we were developing a scientific report, we said that results are the main thing. Carry out a good experiment, but with the poor results, then you end up a poor scientist because you will not have achieved anything. So in our recording, we said that there are various ways you can present your data. One is by table form, and that is what I want to do. So in table form, we can have D to represent dropping height, and we can use maybe a letter like, can still abbreviate it as B, as bouncing height. Why are we doing this? We say that in tabulating any data, it must have a proper heading so that one can easily understand what is going on. Now in this data, the data must follow what the procedure stated. And in the procedure, we said that it will be varying from a height of, you can start from either the lowest or the highest, whichever. They will all do. So you can start from the smallest height, which is 0.5 meters. Remember, units can be either be placed here in brackets, that is in meters, brackets, meters, so that all the writings here we shall know they are being represented by this unit in meters. So we have 0.5 meters, 1.0 meters, 1.5, 2.0, 2.5, 3.0 meters. You can go on up to 3.5, 4 meters, depending on your scope of experiment, the way you will wish to carry out the experiment. Now, by dropping the balls from these various heights, the bouncing height will obviously be recorded, and immediately and sincerely. You may use different maybe machines to record the heights, because it will be a little bit difficult for you just to drop and say there where it has reached. I think that's 1 meter. I think that one is 1.2 meters. No, you may employ some other materials which will also be included under the category of materials. You can see when playing tennis at high level, they normally use video so that they can record whether that ball was out of the court or inside the court. In such a case, you can also use a video that has calibration, so that when it bounces, in that video you can pause and get the height of the ball, then record. Pause, record. Pause, record. So let's assume some figures here. May I pick some that I had here? 50, I used 30, that is 0.3. Now I'm using meters. You can as well use centimeters. In centimeters, you just convert all these meters into centimeters. 100, I used 0.6. You can guess any figures. 1.5, that is 0.96. 2, that is 1.20. Then 2.5, 1.48. 3, we can have maybe 1.87. 3.5, maybe we can have 2.01. 4, we can have 2.42. These are just rough figures. You can pick out any figure, but the best way you can get them is obviously through an experiment. Now, if you have gotten such a figures as data, you have tabulated this data where the height, bouncing height, is dependent on the dropping height, going by what we are seeing. But how would you get to that point? You get to that point after you have moved from the point of results. Now you are at the point of discussion or analyzing the results. So in analyzing, you look at the results, look at the dropping height, looking at the bouncing height, relate those two figures directly. You don't relate like this one to this or this to this. You relate those that are direct, the one that resulted from the dropping, so that you can make a conclusion out of it. And what do you see? From the figures, I'm seeing two direct items coming out. One, the dropping height is bigger than the bouncing height. Is it true? Let's confirm. 0.5 meters dropping height, bouncing height is 0.3. Dropping height is 4 meters, bouncing height is 2.42. So at least it has confirmed. You can only get such if you look at the results keenly. Number 2, what do we see? We are seeing something that is continuous, that the dropping height, as much as it is higher than the bouncing height, but dropping height in all the cases in general is bigger than bouncing height. In general, it is bigger than bouncing height. That is in general. So you will have made a general and a specific judgment. Specific, you looked at just one. This one is bigger, this one is smaller. But again, in general, what are you seeing? You are seeing that dropping heights are always higher than bouncing heights. Now, is there any other way you can present these data? It still goes back to our previous lesson where we saw the aspect of communication. And we said, for you to communicate, there are various ways you can communicate. You can communicate through a table, and there we are. We have communicated using this table where we have seen how the heights are related to each other. But we can also communicate using graphs. Using graphs. Why talk about that communication when you are talking about planning on experiment? When planning on experiment, remember, this experiment is not just for you. It is for you and for others. So when you are planning that experiment, make sure whatever you will get at the end of the experiment, from getting the aim of the experiment until you conclude the experiment, all that you get should be communicated in a proper manner for the others to use or to follow. So one of the other aspects we have to look at is present this data in a graph form. Present the data in a graph form, that is during recording of results. During recording of results, so that when it comes to the time of interpreting the results, that is to discuss and analyze, it becomes easier. Now, when it comes to the graphs, you have to understand that we have two forms of graphs here. There is that graph that will have one discrete item in it. And there is that one that will have two items that have figures on both sides. So, when you are talking about a bar graph, we had also the column graph, we have also the pie graph. These graphs can only work when one of the variable you choose, is a discrete one. Cannot be quantified in terms of figures. Cannot be quantified in terms of figures. But if you get one that can be, the variable can be quantified by figures. This variable of dropping height and that variable of bouncing height is being quantified using figures. Then in such a case, you can use a line graph. You can use a line graph. So here, you can draw a graph based on the dropping height and the bouncing height. And this one, we can try to represent it here, where you can have the two variables on x and y axis. Now, when it comes to representing data on a graph, where we have two axes, that is the y-axis and the x-axis, you also need to identify of these two variables, which one is depending on the other one. They are all variables, but in the graph, you only pick on one to depend on the other one. So the one that is dependent on, the one that is independent, it can work on its own, is put on the x-axis. And the one that depends on the other one is put on the y-axis. In your own judgment, take a few seconds. which one depends on the other one? I'm sure you can realize, or you have realized, that there is no way bouncing, dropping height can depend on bouncing height. You have to start with the dropping before bouncing comes. What does it mean? It means bouncing depends on dropping. So if that is the case, then we shall have our x-axis carrying the dropping height. And automatically, therefore, y will carry the bouncing height. Dropping height, x-axis, bouncing height, y-axis. Reason? Bouncing height depends on dropping height. If you drop at a low height, the height will be smaller than when you drop at a higher height, where the height, if you compare 0.3 and 2.42, this one is bigger. Why? Because this one is coming from this and this one is coming from this, meaning that the bouncing is dependent on dropping height. Then you can plot. When you plot, you will realize that if everything was put to a constant, all the other variables were put to a constant, then you are supposed to get a straight line. You are supposed to get a straight line. But remember, in any normal experiment where a human being that is open to errors, you and me, we are always open to errors. We can make an error here and there. You can misjudge that measurement. Because of that, you may find that when plotting these figures on your graph, some will lie on a straight line, but you may find some going a little bit out of the line. So this is where we come up with what we call a line of best fit. A line of best fit. It only comes in when you know very well it is a straight line, but some of the points are off the line. Reason? Errors are always there, and we always have to accept. That's why we always say record the figures sincerely. Now, going to what we mentioned earlier when we were talking about the graphs, we said that a line graph has some particular advantages to whoever will be using them. And one of the advantages is assuming that at this point the dropping height was 0.5. This one was 1.0. This one 1.5. This one 2.0. 2.5. 3. Which means we had the respective points at this point on the y-axis. Then somebody comes out with a question. What will be the bouncing height? What will be the bouncing height if the ball was released or was dropped from a height of 1.2? Looking at your data here, 1.2 as a dropping height does not exist anywhere. But here comes a question. What will be the bouncing height of this tennis ball if dropped at 1.2 meters high? With a line graph, you can comfortably answer that question by just extrapolating to that line of best fit that you had gotten. Then from there, you get the straight line to where it crosses the y-axis. The point of crossing will be the bouncing height, and I'm sure you will be smiling to whoever asked the question that question was so cheap for you because it didn't carry so much work. But indeed, it's not that it didn't carry so much work. It carried so much work. It's only that you had done prior working very well. You did correct recording. You did correct presentation of this tabulated work on the graph for you now to easily get the bouncing height of 1.2 meters. Always do prior duties in any experiment perfectly and sincerely for you to have an easier time when it comes to further questioning later on. Now, having seen the hypothesis where we said that we thought the dropping height, the higher it is, the higher the bouncing height, I think we have now confirmed that the hypothesis that we came up with was indeed right. We also looked at the materials, and in the materials, we had to go back and make sure that we work with the variables, where we only picked on one variable to check, and that was the dropping height. We further went to look for how to record the data, and we saw that the best way to record the data was to go for the table way. And in that table, you must make sure that it has proper headings. After that, we had to look for a better way to present maybe the work. And we did it through the graph. Why? So that we can be able to answer some of the questions like the one I had just posed of what will be the height of the bouncing ball at 1.2 meters dropping height, and we did it comfortably. Now, after you have done all that, you have analyzed. What next? In a report writing, scientific report writing, we are left with one thing, and that is a conclusion. And when making a conclusion, you have to make sure that first of all, it has to be short. 2, it has to be clear. 3, it has to put in mind the aim of the experiment. And lastly, it has to have an idea of what you got as results. Obviously, when you talk about the results, the discussion or the analysis you made on those results. So, what do you think could be the statement of conclusion in this experiment of yours? Take a few seconds, give us. I'm sure you have tried in your own ways. If you are maybe 2 or 3, probably you whispered to each other to find out what will be the conclusion from your neighbor. Let's see what you can pick out to be a conclusion in this experiment. And the conclusion can be a drop. The height of dropping a tennis ball, the height of dropping a tennis ball has a direct relation to the height of the bouncing tennis ball. Let's look at that conclusion. The height of the dropping tennis ball has a direct relation or correlation with the bouncing height of the tennis ball. Does this conclusion have the aim in it? What was the aim? The aim was to investigate the effect of variation in the dropping height of a tennis ball to its bouncing height. Is that statement or is that content in our conclusion? Yes. Where we said the dropping height of the tennis ball is directly proportional or directly related to the bouncing height. So the heading is there, the aim is there. Do we have the conclusion there? The conclusion in terms of what we got when discussing or analyzing? The answer is yes. We have said it has the statement direct relation. Direct relation. So that statement of direct relation is telling us that if it is at a low height, then the bouncing will also be at a low height. If it is at a high height of dropping, then the bouncing will also be higher. This one is higher than this, just like the same way this one is higher than this. So directly related. That conclusion came from our analysis. Does it have the procedure, the results in it? The answer is yes. When you say directly related to the height of the dropping of the ball, then it means you did an experiment by varying the heights, and you discovered if it is at a low height, the bouncing was also to a low height. And if it's at a higher height, then the bouncing was also at a higher height. That can only be said as a statement if you did the experiment. So that shows that you will have stated in your conclusive statement that the experiment had this procedure of varying the heights, and from the variation of the heights, you also got the variation in the bouncing height of those balls. Now, we have been looking at generally how to plan for an experiment, and we have gone through several steps on how one should do that planning, and the main initial point being always identify variables, so that out of the variables you can now pinpoint out or single out a particular variable to follow until after you are through with it is when you can vary that to another one. But maybe to make this clear, we also need to look at roughly very fast another aspect where maybe through that, for those who don't like tennis, maybe you like athletics. So I would like to use that one very fast to give out that, then maybe look at another aspect you have to look at when carrying out an experiment. So in athletics, it is about speed. Who is faster than the other person? But remember, for somebody to move, I'm sure if you have followed these events, Olympics and all that, world athletics championships, you have heard of cases whereby somebody was disqualified, especially things like 100 meters, because probably during the time of running, wind was blowing, and the person was a little bit aided by the wind to move. So you find that the person has moved excessively faster than expected. So they may say that event has been cancelled, you repeat. Why? Because they know in running there are so many other factors. There is that aspect of wind, there is the weight of the person. Look at those who run 100 meters. I'm sure you cannot pinpoint anyone who will look like me. I cannot qualify to be a competitor in 100 meters. I'm light. But I can qualify maybe in something like marathon. They are usually lighter. But these other ones are heavily built because of the muscles, so that they can sprint very fast. You also look at the surface on which they are running. You will find that the surface on which these events are carried on are specially made to create that proper friction, so that friction should not be a point of question marks. Why? That is a variable. Look at the attire they wear. You cannot be in jeans and you are on a track. You want to compete in 100 meters against Usain Bolt. You will obviously fail, because that is not a proper attire for you to be in. That is a variable. Look at the type of food. You have heard of doping. people taking in drugs that can maybe cause too much energy to be produced within a short period to make somebody to have undue advantage against the others. So they also have to check on the food. That is a variable. And so many others. So if you want to say person A is faster than the other one, all these variables must be controlled. What we call controlled variables. Same type of food, no chemicals, same turf, same attire, same everything. When they say on to your marks, they hit a pistol so that all of you can get it at the same time. They don't use a piece of mouth, because if maybe they use a piece of mouth, the one closer to the person stating the statement might hear it faster and accurately to get up very fast before the other one gets it. So using a pistol, all of you get it at the same time. That is just an aspect of getting controlled variables to only test on one, now the speed. And there you will have done your experiment very well. One thing you have also to note, and that's why I've picked on athletics and particularly on 100 meters, the finishing point is important. When doing an experiment, how to complete that experiment is very important. Imagine of a case where when these people are passing that finishing line and we don't have an item, a machine, an object that can easily pinpoint that Usain Bolt has come out to be the best, the fastest. What will be the result? Chaos. Chaos will arise because these people, as they were running, they could not be easily be in a position to tell that I'm faster than this other person, unless you are far away like Usain Bolt usually is. But the others are usually very close. So you need a machine to exactly, accurately pinpoint who is faster than the other one. So when you're doing an experiment, like the one I talked of, the bouncing tennis ball, you have to get a machine to accurately give you. If it is not that, maybe there are other experiments, even if it is measurement of whatever, measure it to highest accuracy for you to achieve good results. So what am I pinpointing to? Accuracy is important in recording for you to get good results, and also during planning of the experiment. Before you start off the experiment, identify which object, which machine, which procedure, which system will I use to qualify my results, so that I can at the end say whatever I've gotten is surely accurate. And lastly, as I complete my lesson, when planning for an experiment, safety is important. Safety is important. If you know the experiment can be having some particular challenges in a way, look for a way on how to make yourself safe. And even if it is not making yourself safe, making the experiment safe, because the experiment must also be safe in a way. If you know a certain environment can cause a problem, then look for a way to control that environment so that you and the experiment are safe. That marks the end of our lesson today. Thank you.